we are approaching the midpoint. This is lecture number 10. We're going to review Thévenin and Norton, and then we're going to move on to the good stuff, where we start to talk about alternating current. Thévenin and Norton's theorem tell us that any two-terminal linear source may be represented as either a voltage in series with a resistance or a current in parallel with the resistance. You may recall that the Thevenin voltage is equivalent to a Norton current by a Norton resistance. A Norton current is equivalent to a Thevenin voltage over a Thevenin resistance, and the Norton resistance is equal to the Thevenin resistance. Here's an example with a capacitor. To make it more interesting, let the capacitor have an initial charge of 5 volts. As a function of time, we'll see that the voltage on the capacitor changes. The voltage on the capacitor. We start out here with an initial voltage of 5 volts, and we will increase to some maximum voltage. But at this point, we don't know what that maximum voltage is, because we're not exactly sure what the Thevenin equivalent, looking in from terminals A and B, is. But we can find out in short order. Using our rules, we will remove the load. So conceptually, we're going to think of this as being disconnected. We're going to look into the circuit on terminals A and B with the supply shorted. The Thevenin resistance is equal to 2 in parallel with 5 plus 3. Going to the calculator, 2 inverse plus 5 inverse equals 1.4 plus 3 gives us 4.43 ohms. We can then calculate the Thevenin voltage using a voltage divider with these resistors here. Remember, there is no current flowing in this direction because terminals A and B are open. Therefore, whatever voltage you have here will be the same as you have there. The Thevenin voltage is 5 over 2 plus 5 by 100. 5 divided by 7 equals by 100 equals, that's about 71.4 volts. If we redraw the circuit, we have that 71.4 volt source. We have a resistance of 4.43 ohms, terminals A and B, and now we can add the capacitor and the switch. We'll let that switch close at time equals 0, and this capacitor is 50 millifarads. The time constant, which is tau, is equal to the product of RC, which in this case is 4.43 times 0.05. 4.43 times 0.05 equals, that's about 222 milliseconds. Now, recall the voltage on a capacitor as a function of time is equal to the final voltage plus the initial voltage minus the final voltage, e to the negative t over tau. I think we drew a picture up here where we said the initial is going to be equal to 5, and our V final in this case is whatever V Thevenin was, so our final voltage will be 71.4 volts. And again, it's going to follow this curve here as it charges. So Vc of t is the final voltage, so 71.4 plus 5 minus 71.4 e to the negative t over 0.222. Once again, this equation is a description of this curve where the capacitor starts at an initial voltage, which was given here as 5 volts, and charges to some maximum value, which in this case is the Thevenin voltage that you calculated here. Speaking of capacitors, so a related thought. The final voltage on a capacitor is equal to the Thevenin voltage of the circuit feeding it. The initial voltage, the initial current is equal to the Thevenin voltage divided by the Thevenin resistance. This is what we would see if we were to graph this as a function of time. We start out at an initial voltage, and we have this curve, which we've explored many times before. This is the voltage curve. And we know that we will charge to the Thevenin, which is exactly what we say here. The current will have a curve that looks like this. So this is your initial current, and that is the Thevenin voltage divided by the Thevenin resistance. Another way of saying that is at time 0, we could say the capacitor acts like a short circuit. It has no voltage on it, and the only current limiting is due to the Thevenin resistance. At time infinity, so this is time equals 0, and this is time equal infinity, the capacitor acts as an open circuit. In an open circuit, there is no current. We'll come back to this again, where we say in a capacitive circuit, the current leads the voltage. So we'll talk about ice at some point in the future. While we're here, we should talk about inductors as well. The final voltage on an inductor is equal to 0. The initial current on an inductor is equal to 0. And the final current is a function of the Thevenin voltage divided by the Thevenin resistance. If we were to plot that, we would get a curve that looks like this as a function of time. We would have the current on the inductor, and we would also have the voltage on the inductor. You notice this is completely opposite of the capacitor, where the capacitor started voltage at 0 and then increased. The inductor started current at 0 and then increased. At time equals 0, the inductor acts like an open circuit. And at time equal infinity, the inductor acts like a short. Here you have current, and the current is entirely determined by the Thevenin voltage divided by the Thevenin resistance. Something to notice while you're here. In an inductive circuit, the voltage leads the current. So you have something about Eli, and we have something about ice. That ends our review. We can move on to today's lecture. We started with direct current. Then we moved to alternating current. Soon we will move to power and three-phase. Then we will move to machines. Today you are here. At this point you've learned many things about electronics. You've learned about Ohm's law, power laws, Thevenin, Norton, KVL, KCL, and things like mesh and nodal analysis. And what we're going to do is we're going to apply every single one of those again to alternating current circuits. To get us started, let's look at a sinusoid. Where this is the peak voltage, this here is the angular frequency, and this is the phase shift, where that phase shift is usually in degrees. Our angular frequency, that's omega, is equal to 2 pi f, where f is the frequency of the generator. For example, the line frequency in your house is 60 hertz, which means omega is equal to 2 pi f, which in this case is 60. So omega is equal to 377 radians per second. This sinusoid is produced by an alternating current generator, such as this one. Here we have a north magnet, a south magnet. In green, we have the magnetic flux lines. And into these flux lines, we insert a coil of wire, which is represented by these wires here. And as they rotate, they will sweep out a sinusoid. For example, the voltage as a function of time is equal to 170 cosine of 377 t plus 30 degrees. We already said this was the peak voltage. This was our angular frequency in radians per second, and this was our phase shift. Oh, and of course, this here is the voltage. We can plot this as a function of time. If there were no phase shift, the signal would look something like this. But in this case, there is a phase shift. It's a 30-degree phase shift. It would look something like this. We have a cosine, but it appears 30 degrees earlier than the first sinusoid we drew. If you're curious what's happening inside this generator, we would say 377 radians per second. And we could talk about revolutions per 2 pi radians. We could then go on to say that there are 60 seconds in 1 minute. When you put all this together, you would see that this generator is turning at 3,600 revolutions per minute. And by the way, remember that this here is 2 pi by 60, if that helps you with your dimensional analysis a little bit. Shame on me. This should have been 170 volts peak, and this should have been negative 170. So this is the voltage axis. As you read your text, you're going to come across something called the RMS voltage. And the author gives an equation that looks like this. So 1 over time, integral of 0 to some time, voltage squared of t dt, and then you take the whole root of that. So in calculus terms, that's the root. Here's the mean, and there is the voltage squared, so RMS. You can tell this is an important term because it shows up on our test equipment. Here we see that this meter is a true RMS multimeter. So what do we mean by the term RMS, and how does it relate or differ from the term volts peak? I think the best way to do this is to draw a picture. We start with a DC circuit connected to a light bulb. On the other side, we have another light bulb, except this time our light bulb is connected up to an AC source. So this is our DC, this is our AC. For this thought experiment, we're going to have you stand between the two systems and adjust the power supplies so that there is equal brightness in the DC light bulb and in the AC light bulb. At that point, we could say there's the same power in each bulb. If you were to do this experiment, you would find that the RMS voltage is equal to the peak voltage divided by the square root of 2. So you would find that this peak voltage here, this 170 volt, is related to the RMS voltage by the root of 2. So if we took that peak of 170 and we divide it by root 2, we would find out that that should be a number familiar to us. Divided by root 2. Does that look familiar? So 120 volts RMS. Which means if we were to put a meter here, our true RMS voltmeter, into that circuit, it would read 120 volts RMS. And if we were to put it on the DC side, we would see it would read 120 volts DC, because we've equated the two. When there is equal power in each bulb, we say that there is a RMS voltage equal to the DC voltage. You could follow the calculus if you like. RMS voltage is equal to the root of the mean of the voltage max, we'll use sine in this case, of T squared dt. And if you were to solve that, I think you would find that the RMS voltage is equal to the maximum, so Vmax, over the square root of 2, which is exactly what we did in this thought experiment here. We should recognize that this holds for current as well. So the RMS current is equal to the max current over the square root of 2. If you're curious, the power equations also hold true. So power is equal to an RMS current by an RMS voltage. It's also a RMS current squared by a resistance and an RMS voltage squared divided by a resistance. You'll notice I'm intentionally using V for voltage instead of E. So hold on tight and we'll explain what this means in a moment. All right, folks, hold on to your socks because we are about to go somewhere very interesting. Now, we talked about this generator, and we implied that as the generator turns, it sweeps out this signal right here, and we called that a sinusoid. And we're able to describe it in this here, which is called the time domain, and we made some statements about the voltage, which is to say that peak voltage relative to the effective AC versus DC voltage. What you need to do now is hold all of those thoughts in your mind at the same time and allow us to use some trigonometry. The word of the day is phasor. It allows us to take a signal from the time domain, something with a bit of a phase shift perhaps, and represent that signal on the real imaginary axis. So this green line becomes a phasor pointed in that direction, and the blue line, because it's a little bit late, becomes a phasor pointed in that direction, with the understanding that these things are rotating like so. Conceptually, it might help to go back to this generator. If we were to paint a purple dot on this generator, and then if I were to tell you that this generator has a certain length and it has a certain angular position, we would end up with something resembling a phasor, where this has length and there is an angle associated with them. Our green waveform is seen to have an angle 0, whereas our blue waveform is said to be delayed. It has a phase shift. You've seen this before in trigonometry, where you had the real axis and the imaginary. Then you had some hypotenuse at some angle theta. We described the real piece as cosine of theta, and we defined the altitude as j, maybe used I, but we can't use I in electronics because I is already taken for current, so we use j. Anyway, j sine of theta. You may even recognize this as e to the j pi plus 1 equals 0. That's something called Euler's identity, which allows us to make the statement of e to the j theta is equal to cosine theta plus j sine of theta. Anywho, maybe you knew about Euler's identity and maybe you didn't. If you didn't, that's all right. Just know that we're going to come back here. We are going to perform our calculations using diagrams that look like this, and we are going to lean very heavily on our calculators. If you don't have this calculator, I would encourage you to get it. There are others that can certainly do the task, but this is the one we'll be using in the class as we move forward. To get us started, let's go to Mode, and we're going to shift our calculator into complex mode, which is 2. Right there, you'll see that we are in complex mode, and you should also see a D for degrees. So we're running degrees in complex mode. Let's look at these phasors again. We have the real plane, the imaginary. We have a line. That line has an angle associated with it. Technically, these have arrows. We would call the length of this line a scalar. And we would talk about the angle. So you could say a phasor has both magnitude and direction. If you've taken some physics, you'll recognize a phasor is nothing more than a vector. Again, where a vector has length, it has a scalar component, and it has an angle component. So both magnitude and direction. Here's an example. We talked about a voltage being 170 cosine of 377 t plus 30 degrees. We can plot that on the real imaginary plane as a line segment with length 170 divided by the square root of 2, I'll explain that square root of 2 in a minute, at an angle of 30 degrees. We would also say that it rotates in this direction. So we have a line segment of length 120 volts at an angle of 30 degrees, rotating in a counterclockwise direction. By the way, this root 2 implies RMS. So remember, volts RMS is equal to V peak over root 2. So that's where I got this 120 volts from. And for our purposes, we will assume that phasors are always in the form of RMS. Why do we do that? Well, part of the reason we do that is because when you go to measure it, your meter reads everything in RMS. So we may as well make life easier for ourselves. All right, so clean it up. Again, we have the real, the imaginary. We had a voltage of 120 volts. It had an angle of 30 degrees. There are two different ways we can express this. In the polar form, we would describe a voltage, we're going to put a bar over the top to signify that it's a vector, is equal to 120 volts at a phase angle of 30 degrees. In rectangular form, we describe a voltage that is 104 plus J 60 volts. Now, I've asked you to do a couple of these problems already. You may have been wondering why all the trig. Well, if you were to solve this triangle, if you knew the hypotenuse was 120 and you knew this angle was 30, what are the lengths of the other sides? And you would find they are 104 and 60. Your calculator can do this equation very simply. Notice you're in complex, and we're in degrees. We would enter that as 120, shift, and now you're looking for a purple angle right here. It's an angle in purple. See the degree symbol? So 30 degrees. And there it did the calculation for us. So 104 plus 60J. And if you wanted to go back, you would go shift, complex, and number 3 puts you back into polar. And there we are, 120 volts at an angle of 30 degrees. Let's take a look at another example. Suppose you're given a voltage of 120 volts at a phase angle of 0 degrees, and you're given a current of 4 amps at a phase angle of negative 20 degrees. If we run this through our calculator, we have 120 volts. Well, we don't need to do that. It'll just be 120 plus 0J volts, and our current will be 4 shift angle negative 20 equals, so that's 3.76 minus J 1.37 amps. So again, this here is polar form, and this is rectangular form. If we were to plot both of those on the real imaginary plane, our 120 volts at angle 0 would be here. So 120 volts, phase angle of 0 degrees. Our current vector would be about here. And not exactly to scale, but that's all right. So this would be 4 amps at a phase angle of negative 20 degrees. I did say we were going to lean on our calculator. Hold on, we're going to do that in one moment. You'll recall Ohm's law looked like this in DC circuits. Well, it just changed in AC circuits, so now we talk about a voltage vector over a current vector over something called an impedance vector. Our power law changed as well. So here we had pi. Well, that just transformed into complex power over the complex conjugate of the current vector multiplied by the voltage. By the way, this complex conjugate basically means flip the sign for our purposes. If we move back up to this example, you were told that there is a voltage and a current. With voltage and current, you can certainly calculate this new thing called impedance. So let's give that a try. So we know that impedance is equal to, so we do the cover-up method, a voltage vector over a current vector. And I believe we said it was 120 volts at a phase angle of 0 degrees over 4 amps at a phase angle of negative 20. Again, this is where we lean on our calculator. We would enter that as parenthesis 120. We don't need to, but we'll put the angle in there. So 120 degrees, or excuse me, 120 volts at a phase angle of 0 degrees divided by parenthesis 4 at a phase angle of negative 20. And we hit equals. That tells us that the impedance of the circuit is 28.2 plus J 10.3. And impedance is in ohms. While we're here, we may as well figure out the power. So the complex power is equal to the complex conjugate of the current. And we said that just meant we're going to flip the sign. So that's 4 at a phase angle of 20 multiplied by the voltage, which is 120 volts at a phase angle of 0. Moving over to the calculator, that's 4 phase angle 20 equals times 120. We're going to shift that into the polar mode. And we would see that that's 480 what are called volt amps at a phase angle of 20 degrees. That was a bit of a look ahead. We'll come back to this power stuff another day. Before we leave, I want to do a quick look ahead to this thing called impedance. And impedance goes something like this. Suppose we have an AC circuit, and let that circuit have a resistor, a capacitor, and an inductor all in series. We'll let this be 120 volts, phase angle of 0 degrees. Let the resistor be 10 ohms, the capacitor negative J 10 ohms, and we'll let the inductor be J 30 ohms. If you look at that, you'll notice the capacitors are negative creatures. On our real imaginary axis, we would talk about resistors living on the real axis. We would talk about inductors as being, we would talk about capacitors as being negative imaginary creatures, and inductors as being positive imaginary creatures. From our knowledge of series circuits, we can do a guesstimation here, and we could say that the total impedance is equal to the sum of all of the elements. So Z total is equal to 10 minus J10 plus J30, which gives us a total impedance of 10 real plus J20. If you got that far, you could use Ohm's law. You could talk about a voltage is a current multiplied by the impedance, which means you could solve for the current in this circuit as, again using the cover-up method, a voltage over an impedance. Since it's 120 volts, you could say this is equal to 120 over 10 plus J20. So the current is equal to 120 divided by parenthesis 10 plus J is right here, plus J20 divide equals, syntax error. Syntax error because your J's have to go in the end. So 120 divided by 10 plus J20, there we go. That would give us a current of 2.4 minus J4.8. And that is technically true, but I would recommend you put your current into the polar form. So shift complex 3. That gives you 5.4 amps at a phase angle of negative 63.4 degrees. Now, the reason we put ourselves into polar form with current is because this is what the meter reads. Once again, we've gotten ahead of ourselves. Know that this material will be with us through the next couple of chapters. At this point, the real takeaway is make sure you can do these types of calculations in your calculator. Make sure that you can convert from rectangular to polar. Make sure that you can multiply, divide, add, and subtract those rectangular numbers. Get to know your calculator. That will be very important as we move forward in this class.